Right. Hello, everyone. Welcome to Bureau of Reclamation's Crack the Case Challenge webinar. Thank you for taking the time to join us today. Please feel free to say hello in the chat. Let us know where you're joining us from. Our agenda for today will be to provide an introduction of our panelists, then an overview of the challenge, along with how to enter and submit your solution, and then we'll move into the Q&A portion. So just please note, please submit your questions for the Q&A to the Q&A box that you'll see on your screen. We may not get to all the questions on today's webinar. For those that we don't, we'll respond to them via the challenge page, and we'll also be uploading a recording of today's webinar to the challenge page. So starting off with introductions, I'm Andrew Osansky, a project manager with HeroX, and we are partnered with Bureau of Reclamation to administer this challenge. I'm now going to pass it over to Evan Lindenbach to begin the introductions for the panel team.
Thank you very much, Andrew. I'm Evan Lindenbach. I'm a civil engineer with the Bureau of Reclamation, and I will pass it over to Christine next, please.
Hello, I'm Christine Van Zomeren. I'm the prize competition program administrator. So I run the umbrella program that this fits under, and I will pass it over to Brett.
Hi, my name is Brett Lingwall. I am a subject matter expert in geotechnical engineering at Reclamation, and one of the panelists, Carolyn.
Hi, I'm Caroline Bakovich. I work at the Bureau of Reclamation in the Geotechnical Laboratory and Field Support Group with Evan. And yeah, I'm a geotechnical engineer. And I will pass it on to Miriam.
Hi, I'm Miriam Johnston. I'm a geophysicist with the Bureau of Reclamation in the Engineering, Geology, and Geophysics group. And I will pass it on to Chanel.
Good afternoon, everyone. My name is Chanel Smith. I am an Open Innovation Advisor with COSI, the Center of Excellence for Collaborative Innovation at NASA. And I'll pass it to Brett. Have you gone?
I did.
Manel next.
Oh.
Yeah.
I think
It's
Manel is next.
probably me.
Yes.
Yeah.
Hello, I'm Manel Parek. I am a geotechnical engineer at the Army Corps of Engineers Risk Management Center. I'm also a risk advisor, and I sit in Lakewood, Colorado.
Excellent. Well, thank you everyone for the introductions. We'll now have Evan provide an overview of the challenge.
All right, thank you, Andrew. Please bear with me while I share the screen. All right, is that showing up?
Yes, we can see it. Looks great.
Perfect. Well, first of all, just thanks everyone for tuning in. I will be giving the overview of this challenge, the Crack the Case. This is kind of my technical credentials. So I work in the Bureau of Reclamation's Technical Service Center, essentially a fee-for-service A&E arm of the Bureau of Reclamation, solving interesting engineering and science challenges. So let's try that. My presentation cadence will be as follows. We'll start with the discussion of why this is important. Then we'll go into why has this not been solved. Then the ask from you all. And then into the challenge structure, and then kind of some broad thoughts on why I think it's interesting to compete in this and why I think it's important to compete as well. So first of all, why is this important? Well, really what we're talking about is the potential for cracking in earth and embankment dams. And I'm not talking about the wide open fissures that you can see down and they go way deep in the earth. I'm talking about narrow incipient cracks, often without a surface expression. These things are really difficult to detect. And these cracks can be located longitudinally, as we can see in this picture, longitudinally along the axis of the dam itself, so between abutment to abutment. Or we can have transverse crackings, which is the more important type of cracking, where these cracks extend upstream to downstream. And these can be very narrow. These are exaggerated in these pictures. And there can be a number of different reasons that these form, which we'll touch on in a second. But these are, again, really difficult to detect. And these undetected cracks can be internal erosion pathways, which can facilitate water movement along these cracks, which can cause widening and lengthening of these cracks, leading to adverse performance of the dam and potentially loss of water. The current approach that we take now is we use our best engineering judgment, and we may modify a structure. We may try to fix a structure just if we think that these cracks exist. We can't necessarily know for sure that they exist, but if we conjecture enough and believe the risks are high enough, we can go in and do a proactive modification. And this can be expensive. This can be millions to tens of millions of dollars worth of work, based on what we think exists. So how do these cracks form? Typically, these cracks are forming in, again, an earthen embankment, usually due to settlement within that embankment. And generally, it's some amount of differential settlement. So what we're saying with differential settlement is that part of the dam is settling differently or more than the other part of the dam. So we have a couple of schematics of this. I just want to point out all the schematics and this write-up is essentially distilled down from what's on the website. So there's more detail. There will be no test at the end of this webinar on this engineering. So please review it on the website. But again, differential settlement can cause this cracking, low stress zones where we have soil arching, benches or steep walls in the abutments, benches in the foundation, narrow trenches, layers of poor compaction. Again, the idea of parts of the dam settling differently than other parts, leading to the formation of cracks. So why has this not been solved? Well, I think the best way to talk about this is just to look at some pictures of what these cracks actually look like. And you'll notice that these pictures are excavations of these cracks. We're not looking at geophysical data necessarily. We're actually having to do an invasive excavation of the crack to make sure that we understand if it exists or does not exist. And you can see these are relatively narrow, discontinuous features. They can have essentially zero aperture or be pretty tightly closed. This is hard to find. And you can see in these pictures, we might even have to flag them or have them called out with tape. Sometimes these cracks are grouted. They can be narrow and they can be very difficult to find. And I think that points to why it's hard to find them. So our typical tools used to find these cracks are generally either what we would call invasive, like drilling, but drilling could be complicated and could be hard to locate one of these features, or non-invasive using geophysical techniques like electrical resistivity tomography, seismic refraction, seismic surface wave methods, GPR, or electromagnetic conductivity. And that really leads us to the knowledge gap that we're trying to manage here with this prize competition. We are looking for ways to find these narrow, discontinuous, or deep cracks. They're very difficult to locate with our current tools. Our current tools may have issues with a variety of different ground or surface conditions where we can get coupling or not necessarily get coupling of these geophysical tools. We'll talk about in a few minutes. Some tools may work well in dry soils. Some tools may work well in wet soils. And that can be a knowledge gap for us as well, something that works in both of these. The cultural interference of essentially discontinuities in that soil mass, so pipes, conduits, concrete, can be complicated and can cause issues with our geophysical tools. And then in the end, as we saw with all those pictures, the best verification is to actually go out and excavate and make sure that we can find these things or prove that they're not actually there. So to have non-invasive tools that we could do that would be more ideal. In those cases where we have an excavation, we may have a reservoir restriction or an operational restriction to make sure it's safe when we perform an excavation like that. And ideally, we wouldn't have to do that. So again, non-invasive tools would be more ideal. So all of that the discussion of what these cracks are, how they form, our current methods, and then the knowledge gaps, that it really leads to this ask. What are we asking of the folks on this call, and what are we asking of the folks who are interested in being solvers on this challenge? Well, really, we have a couple of primary must-haves, and first and foremost, pretty straightforward: detect and locate cracks. We want tools that work both in homogeneous or zoned embankment dams. So homogeneous dam is just essentially the same soil type from upstream to downstream, whereas a zoned embankment just has a fine-grained core and then increasingly coarsening zones moving outwards from that core in a more modern configuration. And then the idea that deeper detection capability strengthens competitiveness. I think all of these are pretty straightforward and would make sense. Our desired capabilities would be a tool or set of tools that helps us find cracks or prove that cracks do not exist up to depths approaching about 50 feet or more, and ideally with better near surface resolution, something that works above water and underwater, something that works on upstream and downstream embankment faces, that needs to work on a diverse set of ground surfaces, such as soil, asphalt, and riprap. Riprap being those very large blocks that we would have on the upstream face of our dam to protect the soil against wave action caused erosion. We'd like something that has a lot of flexibility in deployment scenarios and works in a lot of different situations. Definitely needs to not harm the embankment. Obviously, the best way to find cracks is to dig the whole thing out, but that's not really the point. And then we really want something that will help us define the extent and interconnectedness of these cracks as well. So finding if the cracks intersect, if they go all the way from upstream to downstream, or if that crack is just a discrete point. That helps inform our understanding of how we expect the structure to behave. Broad structure of the competition. Again, see the website for more detail. The competition is set up to be a 3-phase competition. Phase 1 is a white paper. So up to 7 winners can win $30K per winner for this white paper phase. Phase 2 is the solution development and validation with up to 5 winners with $20K per winner. And then phase 3 is an actual laboratory demonstration and performance assessment. And the first place will win $60K and the second place will win $30K. So it's a multi-phase competition, which I think it makes it really exciting. We can put great ideas to paper and then develop these ideas and actually demonstrate them in a laboratory, which is really unique, I think, to this prize competition. And then some final thoughts on why I think folks would be interested in competing. Number one, first and foremost, this is a pressing dam safety challenge. This is a question that our agency has, that other agencies have, and in this time of water and needing water, we need to make sure that we can support public safety and provide good water reliability. Hopefully, through this competition, you develop a marketable solution. This competition, again, is multi-agencies, so getting a lot of exposure to other agencies with the proposed solution. This does provide the ability to demonstrate the solution in a laboratory, and in our laboratory in particular. We'll give you recognition within the industry, and then bottom line, this is a fun technical challenge. These things are really interesting to work on, and it would be great to work with you all on trying to solve this pressing dam safety challenge. So with that is the conclusion of my slides, and I will hand it back over to Andrew and then be happy to answer whatever questions you all have.
Excellent. Thank you, Evan. Yeah, just a quick reminder before we screen share show you the challenge page. Please do enter your questions for the group into the Q&A box at the bottom of your screen. I'm going to go ahead and share the challenge page. All right. So this is the challenge page, herox.com/crackthecase. It's where you're going to find all the information about the challenge. We do recommend you take some time reading the summary, read all the details there. That's going to let you know everything you need to know about the challenge, how to participate, and what we're looking for there. In terms of the timeline, please do note that the submission deadline for phase 1 is coming up on April 30th. So please do note that date. Additionally, we do have resources which complement the summary section and provide some additional information for the challenge. If you do have any questions following the Q&A webinar today, please do feel free to add them to the forum and we will answer your questions there as well. When you are prepared to go ahead and make your submission, please go ahead and click solve this challenge. You'll then be able to create your HeroX account if you don't have one already, and then you'll be able to access the submission form. We did want to just share a reminder, which is overviewed in the summary section. For phase 1, you'll submit a 12-page concept paper that's describing your proposed solution and your team's ability to carry it forward through design, development, and demonstration in later phases of the challenge. So we do recommend following the challenge and getting access to the submission form so you can review that and take a look at what you'll be submitting. All right, we are now going to move into the Q&A portion. And I'm just going to go over and check out our first questions here. All right, first question for the group. Concerning application of the winning solution, what type of engineers will be applying the solution?
That is a good question. I will take a first pass crack at this. I think it would be a broad range of folks. So if we were to actually implement this here at the Bureau of Reclamation, depending on the solution type, we could involve electrical engineers, mechanical engineers, geophysicists, and civil engineers. But it's hard to answer too specifically without knowing kind of the broad category of that solution type. But I can say at our organization, we have folks in all of those various disciplines.
Excellent.
Any other thoughts from the panelists? Please feel free to speak up, other panelists. I'll try to take a first crack and throw something out there, please.
I don't know if, Evan, you said geologists, but they play a pretty important part in helping us understand the subsurface materials.
Thank you, Manel.
Excellent, thank you. All right, next question. How confident are dam safety engineers in predicting where on an embankment cracks are most likely to form, even if they can't confirm whether one exists?
I can answer that. This is Brett. As far as simulation tools, modeling tools, as well as common sense assessments and evaluations based on geometry, 2D and 3D superficial and subsurficial conditions, we're pretty good. So we're pretty good about estimating, calculating, simulating where these things should be or should not be. The questions are about these about the detection methods is to either we think we have a problem, we need to go confirm without digging the embankment apart, because as we dig into embankments, it increases dam safety risks. So we don't want to do that. We want non-intrusive methods to confirm that things are where we think they might be, or to confirm that they're not there and that the simulations might be wrong. Or for screening tools for special unique conditions in which conventional simulation prediction tools would not cover hyper site specific conditions that we would not be aware of until we would do the detection, identify there's a crack, and then we could probably and reasonably in most cases back out the causal mechanisms from those hyper site specific conditions.
Thank you, Brett.
Thank you, Brett. Right. Next question. When you talk about cracks being millimeters wide but dozens of feet deep, is there a sweet spot in terms of crack size and depth that would be most immediately useful to detect?
That's a good question. Miriam, would you have thoughts on that as our resident geophysicist?
I was gonna say this might be a better one for an engineer in terms of at what point does it become the most pressing matter if you've got, three dams with three different size cracks, which one's the most pressing? But in terms of like the standard geophysical methods that we use, when it's I think the crack that we're most concerned about is the one that is too small for us to see based on our resolution. So like a lot of our methods we can see with like the seismic and the electrical resistivity, we can get down to like 2.5 feet or even half-foot resolution, but getting smaller than say a half foot and still being able to see at a significant depth is lost in those methods. And if you switch over to GPR, you can see the smaller cracks, but then your depth is definitely even more limited, especially once you get into the clayey soils. So I don't know that I have a good answer as to a specific sweet spot, but something that's on the millimeter or centimeter, even inches, but at depth is then becomes the issue with a lot of the methods that we're using traditionally.
Manal, from the risk perspective, do you have thoughts?
Yeah, my thoughts from the risk perspective, and this is a very simple answer, but the smaller the better. If we can identify the smallest of cracks, then we can use our other information and discipline knowledge to help us determine what we think the likelihood of that crack, what the likelihood is that that crack would open more and result in an internal erosion failure mode. So like the last question that was asked, we have some pretty good ideas of where these things could happen, but really what we're looking to do is help, from a risk perspective, help our subject matter experts be able to assign a likelihood of the crack being there and then a likelihood that that crack would proceed to grow over time. So change detection is important here too. So that's why, the smaller crack we can detect, then we can also track its change potentially over time. That's another piece, a performance piece that's really important for us to understand the risk of a structure having poor performance that could lead to loss of impounded water or breach. So in terms of a sweet spot, I know my answer was a little bit of a cop-out, the smaller the better, but in terms of aperture, I would say on the order of, several millimeters to a centimeter would be great to understand in terms of aperture.
Excellent. Thank you. All right, next question. Are there any solutions reclamation is not interested in seeing?
Ooh, I think we have those detailed pretty well on the challenge website, and I would suggest going over there to take a look at those because I think we lay that out pretty explicitly, and I don't want to misstep on what we already have laid out there. Any of the panelists want to comment on that one?
Excellent. So yeah, we would just
Sorry,
refer- oh, go ahead.
I would just chime in that I think one of the bigger things is probabilistic models, right? It's not, we know that we're not looking for probabilistic models based on conditions and things. This is about detection, and that is spelled out as Evan alluded. That is spelled out in the guidelines. Thanks.
Thank you, Jamie.
Excellent. Thank you. All right. Next one, it's a bit of a long one, but I think important. Phase 3 will focus on demonstrating solutions in real-world embankment dam conditions. It states in the guidelines, detailed requirements and success metrics will be shared at the Phase 3 launch. However, dependent on the specifics of the Phase 3 laboratory demonstration setup, the prototype could be very different, and only getting that information in March 2027 could make it challenging. Is there a possibility to get this information earlier, perhaps the beginning of Phase 2, or will this be a demo at an actual dam site or using a scale model? So I think the idea is just looking for some more information on what to expect for Phase 3 to inform prototypes in Phase 2.
Sure, and that is a really good question. And I wish I had more detail at this point, but we have not completed our scoping of what that Phase 3 testing will be at this time. We will be endeavoring to get that scope complete as early as possible. I respect the solver's question and the solver's focus that it would be nice to know what they need to do. But my suggestion at this point is to detail the solution that you believe would work given the guidelines that we have laid out, and then it should accomplish what you want it to accomplish in the future.
Excellent. Thank you, Evan. Next question. What is the best non-destructive method that we currently have among electrical resistivity, tomography, seismic, etc.?
I'll take that one. Fortunately, I think the answer is it's site specific or it's site dependent. The GPR method is great when you're trying to look at those smaller aperture or smaller cracks. But we know that a lot of the dams and a lot of the soils used have a significant amount of clay content, even in like the near surface. So being able to see those cracks at depth becomes an issue with GPR. So if you have a crack that's in the very near surface, then that's a great method for that situation. But if you have a clay soil, then you're kind of at a loss with GPR. So then you can try the electrical resistivity or the seismic. But again, getting down to that resolution of seeing those really small features becomes the issue. So if we have a crack that's already expanded and of significant aperture, then those methods do work fairly well, because you can, especially with the electrical resistivity, because there's usually either an air-filled void or a water-filled void. So you can hopefully have that contrast between your void or your crack with aperture and the surrounding soil. But again, that's not always the case, so site-specific. But I wouldn't say there's one method in particular. From my standpoint, I always love to implement multiple methods when we're going out to look at a dam. But if there's, and it's okay to pair, multiple methods. We usually say is like the best way to go, because then you can compare and contrast your results and get a better confidence in what you're seeing. But again, it's very site dependent on, do you have clay soils? Do you have more sandy soils? And what is the embankment made of? What is the core made of? So there's not one good method, one perfect method, but it really depends on the dam itself.
Excellent. Thank you, Miriam. All right, next question. How much do soil moisture conditions and seasonal water levels change the detection problem? And is there a preferred time of year or reservoir condition for running these kinds of surveys?
I'll handle that one. Moisture condition is key to this problem. If we have a crack and it is catching a lot of water, it's such that it's pushing a lot of water into the embankment, it's in many ways too late and we're pushing into some sort of emergency response corrective action. If the crack is there and it's in moist soil, but it's not carrying water, we need to know, because it's not too late. This technology has some applicability. The most important cracks, though, are those that are in dry soils that have not yet caught water. Those are the ones we want to get ahead of and detect with most importance. Because, as I said, again, if it's already caught water and it's pushing water through the embankment, we have our actions, our engineering is very different than detection of cracks that aren't posed, that we think are there, that could pose a dam safety case, but we can't easily detect. So for another perspective, a lot of the geophysical methods work better when there's water flowing through the cracks, because there is a difference in conductivity or velocity or something that has enough, that we can detect with enough granularity with a spatial averaging of the technology, that we can catch it. But as the soil dries and we lose those moisture changes and those influences in electrical or seismic resistivity, or with the shear wave velocities, P wave velocities, because they're dry, we lose that, and it becomes much more difficult to detect. So it is desired that the technology would work in the wet or the dry, but dry would be a significant preference if it was available.
Excellent. Thank you, Brett.
Thanks, Brett. Caroline or Manel, do you have thoughts on that as well?
My thought, and I don't disagree with Brett, that dry and somewhat moist is really important and possibly more important. But even in saturated cracks, it's good to understand if they exist, because the time rate effect of erosion is still not as well understood. So even if the reservoir levels are high, the cracks are saturated, we might still be like, if we can detect it earlier than say we're seeing seepage or a wet spot on the surface, downstream surface, that could still be helpful in my understanding.
So I can add just a little bit to that. Again, I agree with my colleagues. Certainly, the movement of water is important, and the presence of water in a crack is important. But one of the mechanisms for cracking is desiccation. So cracks can be dry, and we still want to know about them because they can be dry at some point, but then when a reservoir rises to the point where they load that crack, then we can have that can cause a challenge. So yeah, just a note there about desiccation.
Excellent. Thank you, everyone, for the insights. All right, we have a follow-up question to the previous question for Miriam. What are the downsides of electrical resistivity tomography? For example, is it expensive, complicated, etc.?
In general, I wouldn't say there is a downside. I guess the biggest downside would be, are you going to see an electrical contrast between your void, your crack, and the surrounding material? And then it does get expensive if you're trying to have a better resolution. So say you bring your electrode spacing closer together, but to still be able to see at depth, you have to make sure your line is long enough. So that does become more expensive, because you have to, have more equipment to be able to decrease your electrode spacing, but keep the line length long enough to see deep enough into the structure. So that does add time and cost to the project. So, it can get expensive. But generally, I think electrical resistivity is not a bad, I think it's a good option, and one that we usually use when trying to image cracks or voids in a structure. So.
I'd like to just add to that, and this is a little bit outside of my lane, so Miriam certainly step in. But my understanding is that electrical resistivity success also depends on the moisture content in the soil. So, for example, if you're in a dry silt condition with low plasticity, maybe electrical resistivity will be more challenging.
Yeah, depending on what your embankment is made of and the material you're trying to image that crack in, if there's no contrast between your soil and the crack, and air, whether it's air filled or water filled, if there's no contrast, then you're not going to see the crack itself. So whether it's a high resistivity material and a air filled void, or a low resistivity material and a water filled void, that does become an issue. Yes, you're right.
Great. Thanks, everyone. All right, next question. Given what's been mentioned, to what extent is change detection of interest for this challenge, or is the one-time dam characterization really the objective for this challenge?
I guess in my opinion, the change detection fundamentally comes down to the accuracy and repeatability of the solution. So if we can assume that the solution is both accurate and repeatable, and our results over time can be comparable, and we can continue to use the solution in a reasonable deployment time frame, then change detection will naturally fall out of that solution's ability. And so then working towards those metrics of accuracy, repeatability, deployability for a reasonable cost should then naturally lend itself to change detection. But I'll open that one up for the panelists. That's a bit more on the nuts and bolts contest side.
I guess just I think I understand the question. Change detection is important to us as, or to me especially as a risk assessor. But I think what we're looking for this challenge is just being able to identify a crack. And then, if we were to study it again, we would be able to identify whether that crack has grown or has sealed itself or otherwise changed condition. So it's, like I said, it's important for us to understand how conditions change over time. But really, what we're asking is for us to enhance our ability to understand whether cracks actually exist.
Excellent. Thank you. Next question. Considering that machine learning is part of the challenge, has machine learning already been combined with one of the discussed methods? And if so, which ones?
Ooh, that one I will punt to the other panelists.
Yeah, we see a lot of that in the literature these days, but we have not done in-depth in-house attempts. Most of what we've seen in literature is fairly early attempts to use machine learning, where the technology and solution we're looking for needs to be a little more mature, rather than first concepts. So machine learning is very welcome, but it needs to be on the more mature side of an application rather than on a first theoretical initial attempt at its application for the geophysical method.
A lot of machine learning applications I've seen they're really good correlation tools. So using multiple physical detective methods and then correlating those. I've seen that in literature recently. And I think Evan and other panelists, correct me if I'm speaking, and definitely look at the webpage for more details. We, I think, outlined this quite a bit in the website. But machine learning is welcome as long as it is using physical methods to detect. Like the baseline of this challenge is we're trying to detect cracks. So machine learning is welcome as long as it's being based off of data from physical detective methods.
Excellent. Thank you. All right, next question. Can the solution be permanently embedded, as an example, made a part of the dam?
I don't see why there would be a reason it couldn't be. I think it would need to be explicitly stated as to why and power sources and costs and kind of all of those things so we could understand the full life cycle of the solution. When it comes to dams, there is a strong do no harm. We would not want to adversely affect the performance of the structure or from the safety perspective or from the operational perspective. So those would be key considerations for us to install something permanently. I think the point also would be it is normal for us to have instrumentation at dams. And so including that in a standard instrumentation portfolio would not be different from what we typically do.
Yeah, just to reiterate, anything invasive, we would take a really special look at. Non-destructive, non-invasive is ideal. But like Evan said, we do have some instrumentation that already exists in our structures. But we would be, I think, a little hesitant to install additional invasive elements.
Thank you. And we do have time for a few more questions. So if you do have any more you'd like to ask, please submit them to the Q&A box there on your screen. All right, next question. How does reclamation currently prevent false positive detection on dry embankments?
I can answer that from a geophysics standpoint on data we collect from geophysical methods. There isn't really a good way to filter out the false positives without getting ground truthing. So in the most ideal world currently, we would collect our data and say, okay, these are the locations where we think there's something going on, and ideally ground truth those, a couple of them, depending on how many would show up in the data. But by basically putting eyes on those areas, so excavating a little bit down to an anomalous feature, and then saying, okay, this is what the data looks like, and this is this area, this is what we see in the real world. Okay, now we can extrapolate that to what the rest of the data looks like and decide, okay, are these other areas going to exhibit the same result, or adjust, like, okay, we based on the data alone, we think these are voids or cracks, and then we can, like I said, ground truth that and be like, okay, we think these ones, based on our ground truthing, these are more anomalous features that could be indicative of a crack, and these ones are not. So from a geophysics standpoint, that's what we do currently.
Excellent. Thank you. All right, next question. How often are embankment dams typically surveyed, or are they usually just surveyed when there are signs of trouble?
I'll answer that. So it changes from dam owner to dam owner. And won't speak for the Army Corps, I'll speak for Army Corps. At Reclamation, all of our dams have an annual site inspection. They also have on a 4 and 8 year cycle a periodic performance review, and they have a comprehensive site exam every 8 years. So they're being looked at every year without some other triggering condition for more frequent inspection at a minimum. They have a fairly rigorous examination every 4 years. And then on an 8 year cycle, they have a thorough, rigorous examination on that 8 year cycle. If there are conditions such as first fill, such as first fill after a modification, or first fill, for a new dam or something like that, or other instances like earthquakes, they may be on a daily inspection routine, a weekly inspection routine. We have various processes in place for special cases. But one should expect at a minimum that these embankments are being looked at visually every year, at least cursorily, and then in depth every 8 years.
Yes, we have a similar type of program, just starting with what Brett said. In large events, large storm events, after earthquakes, that kind of thing, they do inspections immediately, and then probably daily or more than daily, depending on the conditions. And then we do periodic inspections along with periodic assessments. Those are on a 10-year cycle. The dam tenders have a great idea of what's going on at their structure. So they inspect, pretty much constantly if there is, if the site is manned. And then they also do annual inspections. So the big effort is on a 10-year cycle, but that doesn't mean there aren't eyes on the dam much more frequently than that.
Great, thank you. All right, next question. Can you clarify from the submission form, the section that states provide a dollar amount that represents the estimated total development and full-scale solutions costs? Is that the cost to the proposer of developing the solution? Is that the cost to the proposer of developing the solution? So I guess the question is, what are we looking for? A further definition of what the dollar amount should represent.
I think the silence on the call indicates we can't really answer that.
I think it's one we could come back to. We need to. Yes. Okay. So we'll take that and we'll clarify it on the challenge page. All right. Another question from the submission form. Describe a realistic deployment and operation scenario and the time and cost you envision being required to successfully operate your solution. This seems to speak to just the cost of the dam owner for deploying the solution. Can you confirm that this is correct? It's along the same lines. I don't know if this is another one we wanted to take offline, or we could try to answer that here if there's some thoughts.
I think we could describe the deployment scenario. Maybe that's the reasonable start. Maybe Miriam starts with the deployment scenario of what that looks like in the field. And then we get some thoughts from Manel and Brett on how they would analyze those or think about those data in the risk analysis.
So just to clarify, though, Evan, before you all answer, I think that's reasonable. I just want to clarify that is an excerpt from the submission form. So the solver is asked to describe a realistic deployment and operation scenario and the time and cost that they would envision being required to successfully operate their solution. So if there's an example scenario that you all would like to give, I think that'd be great. But just to clarify that came from the submission form. Sorry.
Interesting. Thank you.
Yeah, I see it as describe how you're going to take your instrumentation and deploy it out in the field. So you have your hypothetical embankment, describe what deployment of your instrument on the embankment looks like and how you're going to operate it, how you're going to collect your data on your embankment, and then whatever data processing is involved in that, and then the cost of that. So like I know if I'm going to go out and do a seismic line that's 1,000 feet long, I know roughly the cost of what it will take to go out and collect that data. That's how I interpret that.
Excellent. All right. And yes, we will on the previous question in this one, we can get back on the challenge page. Any further detail that we do discuss around the cost area. Excellent. All right. And again, if there are any further questions, please add them to the Q&A box. We're getting close to wrapping up. So if you have any final questions, please get them in now. All right. So next question, if a team's approach works well at shallow depths but has limitations deeper, is that still valuable to reclamation, or is deep detection the real priority?
I think the interest is detecting all cracks, and I think in my mind, and I think the way we have things laid out is that the desirable is to detect cracks up to about 50 feet below the ground surface with increasing spatial resolution towards the surface. So the expectation being, yes, we understand that there will be more interference or more complication with deeper detection techniques, but ideally closer in that near surface area, we could have finer resolution. I think part of that goes back to the point by Manel with the desiccation cracking, and then the point by Brett of these untested portions of our embankment that may be up high, and wanting to understand if there are cracks that exist in areas that do not see water and would have very low spatial variability, which, going back to what Miriam was pointing out earlier, that lack of spatial variability, that lack of something in the crack or differences on the sides of the cracks makes them really hard to detect. With that, I'll punt it to the rest of the team, though.
No, this is a challenge. We'll see what the different teams can give.
Yep.
Well, thank you. All right, next question. Has reclamation seen any promising results from combining multiple geophysical methods on the same site, even if no single method was conclusive?
Yeah, we have seen that where if if we go out and collect, say, seismic and resistivity at a site, and you were to look at just the individual surveys, it may be inconclusive, but when you can compare the results, then the answer is more clear. So yeah, we've certainly seen that. That's why I like to go out and do multi-method surveys when I can, but the cost and sometimes time is usually the biggest concern there, or limiting factor for those.
Well, thank you, Miriam. Well, with that, we've come to the end of our questions, and we're just about at time. So just wanted to, we'll wrap up now. Wanted to say thank you to everyone. Thanks for the very engaging questions. Thank you to all of our panelists for taking the time today. And please do keep in mind that the submission deadline is April 30th. We will be posting this to the challenge page. If any questions come up before the submission deadline, please feel free to post them into the forum, and we'll answer them for you there. All right. Thank you all for your time.